So I'm Emmanuel Gaudin from Pragmalev. I'm the founder of CEO of Pragmalev, and we wrote this paper with my colleague Mihal Brumbulli about industrial operations, and one of the topic here is that in complex industrial organizations, it's very difficult to follow up what's going on. So we had maybe less than 10 years ago request to build some technology or some ways to verify and optimize processes. And the one I'm going to talk about today is, if I can go to the next slide, yes, is a real use case from Airbus aircraft. So their main problem is that because of the number of operations they have to do to build an aircraft, they have a very hard time to evaluate how long it will take to manufacture a new aircraft, and if something goes wrong in the manufacturing process, what will be the impact, the time impact or the financial impact. So that's what we have been working on with them. So the name they give it is the Product Development Plan, and this is part of the DMS, which is a larger project within Airbus about digitalizing everything from design to services. So it's really like R&D, manufacturing the plane, and then maintenance of the plane. So everything in the end ideally will be digitalized. And the main goal, as I said, in that case, is to evaluate the lead time and the associated cost related to the product development plan. So this is part of a project called One Way, which was financed by the DGAC, Direction Générale de l'Aviation Civile, which is the French FAA, basically. And that gathered 14 partners, among them, the biggest companies in the aviation industry, and some service companies and universities. As you can see, the budget was quite big, like 48 million euros for. It was more than 18 months. It was, I think, 24 months total. They worked on a lot of different aspects in the aviation problematic in the aviation domain, but today I will focus on the product development plan. So the first thing about industrial operations is to properly define the process. The basic idea of a process is very simple. It's just a series of actions to do something, one after the others. But of course, if you manufacture something which is complex, or if the organization is complex, it can be really complicated to understand. So very often in these organizations, the process is not properly formalized. Or I should say, it is sort of formalized, but each department has its own way of formalizing it. And so if you want to put everything together, it doesn't, of course, work. It needs to use the same notation so that you can put all the information together and do some analysis. So the obvious choice is BPMN, which is the popular standard to describe business processes. It's standardized by the Object Management Group. And I give you here a very basic example, which is, of course, a fake example. We just made it up for the paper. But here you have, let's say, two one department, or let's say 2 factories. So the main one in Toulouse. And when it receives an order, it tells the factory in Brighton to manufacture the wings for that plane. And then they have to send the wings to Toulouse so that they can fix the wings to the plane body, put the engines, the landing gear, and deliver the plane. So of course it's very, very, very simplified. It's just to show a very basic business process if you have never seen any BPMN before. So to give an idea of the complexity of the model in the use case, it was around 1,000 tasks. So a task is one box. So it can be a very simple operation, or it can be very complex. Usually, if it's very complex, it's what we call a call activity. So it has some further task within the call activity. So a call activity can call another call activity and so on. So in the model we used, we had a depth of 4, which is I guess not the true depth, but gives a sense of the complexity. Around 1,000 events, 725 gateways. So a gateway is that at some point you might have to do things in parallel, or to select a path or another, or any combination of path. So that's what you call a gateway. A gateway can also be related to time. So for example, if you have 2 branches, and if you can have a timeout on a branch, and then you have to you follow up the path of the branch where the timeout went off. So it's quite complex. So you can understand that if you read this, it's for a human, it's not verifiable. You really need some tooling to be able to sort of check what's going on. So at first we had already, when we started the project, we had a tool where you could do some step-by-step animation of the process, so you can verify that things are properly connected and properly finished, and interactions between participants are properly designed, and so on. The tool can also do some automatic exploration. So for example, you could detect deadlocks or unreachable path and things like that. So it's already a good first step to make sure that the overall process is working properly. And while you do that, of course, you have the coverage information to make sure you went through all the path and this is correct. But now the question was about lead time. So then you have to add some information to each task. You have to add how long a task will take, how much money it will cost, or how much energy. And you could, when I say cost, it can be money or resource. And there's a complementary notation called BPSIM to add this information to the BPMN model, which is, let's say, de facto standard. And you can say for each task how long it will take, and use statistical distributions, because of course what happens is when you build something complex, you're not sure of the time it will take exactly. So you can say, oh, this will take like maybe 30 days plus or minus 5 days, and then you can use normal distributions, uniform distributions, triangular, whatever. There's a bunch of distributions available in BPSIM. Also, BPSIM allows you to define scenarios. That means you can say, I have one plane order every month, or every 2 weeks, or every week, and they will run on top of each other, of course. And the resources required to manufacture the plane might not be available for the second or the third or fourth plane, and it will take this into account in the scenario. And last, you also define what you are expecting to see as a result of this simulation with BPSIM. So that's something we worked on in this project. We developed, and the interesting thing is that this simulator, which is sort of statistical simulator, is based on the execution engine based on BPMN semantic, which is a guarantee that the simulator is conform to the BPMN logic. And I'm saying that because there are other process simulators, but actually they don't use the BPMN semantics, and so at some point you're not sure that what you're simulating is correct. So once you run a simulation, what happens actually is that you don't have to do anything. Everything is automatic because each gateway has a statistical probability to go one path or the other. Each task has a time drawn by the statistical distribution. So everything sort of go automatically to the end. But then, of course, because if it's statistical, you have to run this several times, what they call replications. You have to repeat that again and again to converge to a result. And that means at the end, you have a lot of information to sort of analyze. And you need some post-processing for analysis. So I'm just giving you like some rough things we did where you can have the result of the time it takes if you have the wings travel by boat, by plane, or by train, which again is a dummy example, but just to give you an idea of the kind of result you have. In the project One Way, Airbus developed their own sets of analysis tool to properly present the information. But one of the important thing, and only the simulator could do it, was the critical path. Because when you want to optimize an execution path, of course you have to optimize where the lead time is. And the simulator can show graphically with a heat map where the critical path is. And because it's also a distribution, it's not like 100% up there. I don't know if you see my cursor, or 0% down there, but it can be 80 or 20 or 70 or 30. So it's also a statistical information we need to represent, and the heat map is a good way to represent that. We actually later after this project we also did a tool to generate the critical path out of an activity diagram, because activity diagrams are sometimes used to describe processes, but they lack some let's say, I could say execution semantic and some information, but you can import this and run the simulator and get some critical path results. Another thing is about the resources, because as I said before, maybe if you have a lot of orders, some resources will be a bottleneck, and you want to identify them so that if your lead time is too long, you can maybe add some more resources, or maybe change the process in another way so that it's not a bottleneck anymore. But anyway, you get the information out of the simulation to be able to analyze that and reallocate the resources, which is a key thing in industrial processes. Another aspect that was explored was the variability. So you can imagine that if you order a plane, you have a lot of options possible. I don't know, maybe you want to have movies inside, or maybe you have a special landing gear, or maybe whatever. And all these options sometimes are not compatible, so you have to be careful not to put them together. But also they have an impact on the overall process. So the idea was to be able to explore options and see the impact on the overall lead time. So you can imagine, for example, that you could tell a customer, "Oh, I can deliver this plane with full options as you required, but it will be like maybe in a year. But if I remove some options, so maybe it'll be available in 6 months." So I mean, it's like up to you if you're okay to wait for another 6 months. So there has been a lot of work with that. And so this was work done with the University of Rennes and Airbus, and they used the process as an input and did some variability, and they generate a resulting process, PPMN, and run the simulation and get the result for each variability. So we were like a brick in the overall tooling that was developed in this research project. And last but not least, because I think it gathers everything, was let's say work on how a digital twin would ideally work. So because you have a model of the process, so when the process is ongoing, you can gather information, real timing information from reality and put it back in the model. And then you can say, oh, this is not conform to the process I was planning to do. So maybe some tasks are not properly done in the right order. So, okay, but mainly maybe a task is late or very late or not possible because of some technical reason. And what's the impact? So then you can rerun the simulation from that point. So you have some real data and then explore some new solutions. And maybe reevaluate, reassess all the resources and everything, and try to mitigate and reduce the lead time. So that's sort of an architecture we did. Because out of this project, basically, the execution and simulation engines are sort of mature. I mean, they are available in industrial products. Like the other ones are more research thing. So as I said, we have explored other input formats for the business process, such as the activity diagram, but it could be some other representation. We were thinking also to introduce some variability features in our editor, because it's very difficult to deal with variability. I mean, there are two ways to do it. You can either add basic features to build up your system, or you can build a process with all the features together and then take them away. So it's like positive variability or negative variability. And but at the end, what you want to see is what happens when you have decided which features you want in your process. So anyway, it would be interesting to introduce that in a proper editor to ease these variabilities. And also we are planning to work on improve the digital twin capabilities, but that's quite complicated. So we would like to have a real use case to work on this. And that's it.